A tiny machine, built by human hands, hurtles through the silent void of space. Its target is a mountain of rock and ice, a wanderer left over from the birth of our solar system. Then, in a flash of brilliant light, they meet. This is not the stuff of science fiction. It is the reality of planetary defense. We are learning to push asteroids. The act of a spacecraft hitting an asteroid sounds simple, almost blunt. But within that single moment of contact lies a universe of complex physics, a story of energy, motion, and change. Yeah. The journey to impact is a long and precisely calculated one. It begins years before the collision, with scientists and engineers on Earth plotting a course through the solar system. The first phase is the approach. The spacecraft, guided by commands from mission control, travels millions of kilometers to intercept its target. This is not a simple point-and-shoot operation. It requires navigating the complex gravitational pulls of the sun and planets, making tiny, precise adjustments to its trajectory using small engines called thrusters. The spacecraft is essentially threading a needle in the vastness of space, aiming for a moving target that is itself hurtling along its own orbital path. As the spacecraft nears its destination, when the spacecraft makes contact, the laws of physics take center stage in a dramatic display. The core principle at play is the conservation of momentum. Momentum is a measure of an object's motion, calculated as mass times velocity. Mass. Velocity. When the spacecraft hits the asteroid, it transfers its momentum to the larger body. Think of it like a billiard ball collision on a cosmic scale. The fast-moving but small spacecraft imparts a push to the slower but much more massive asteroid. This transfer of momentum is the primary reason the asteroid's path is altered. The goal is not to destroy the asteroid, but to give it a gentle, precise nudge. This collision is anything but gentle, however. The incredible speed of the impact means that a vast amount of kinetic energy, the energy of motion, is released in an instant. A significant portion of it converts into intense heat. A significant portion of it converts into bright light, creating a brilliant flash that can be observed by telescopes millions of kilometers away. This flash is the first sign that the impact was successful. The energy also works to excavate the asteroid's surface, vaporizing rock at the point of contact, vaporizing metal at the point of contact, and blasting material outward. The spacecraft itself is completely obliterated, becoming part of the cataclysmic event it was designed to create. The immediate result of this energy release is the formation of an impact crater. The size and shape of this crater depend on several factors: impact speed, collision angle, composition. If the asteroid is a solid, dense rock, the crater might be a relatively clean, bowl-shaped depression. However, if the asteroid is a loosely consolidated rubble pile, the impact might be more like hitting a giant sandbag. The energy would be absorbed differently, potentially creating a much larger, messier crater, and sending a far greater amount of material flying into space. The material blasted away from the crater is called ejecta. This cloud of dust, rock, and debris shoots out from the impact site at high speed. As this material flies away from the asteroid, it creates a recoil effect, much like the kick from a firing rifle. This recoil provides an additional push to the asteroid, amplifying the initial nudge from the spacecraft's momentum. In the case of the DART mission, scientists discovered that this ejecta recoil was a much more significant factor than they had anticipated. Yeah. The work of science does not end with the collision. In fact, for many researchers, that is when the most important work begins. A global network of telescopes on the ground and powerful observatories in space turns its gaze toward the target asteroid. The primary method of observation is photometry. It involves measuring the brightness of the asteroid system over time. For a binary like Didymos and Dimorphos, Astronomers time how long the smaller moon takes to pass in front of or behind the larger body. By measuring eclipses before and after the impact, they calculate the new orbital period with incredible accuracy. Visual aid. A diagram showing how ground-based telescopes measure the change in light as Dimorphos orbits Didymos. Another critical tool is spectroscopy. Sunlight reflecting off the asteroid and its ejecta carries a chemical fingerprint. Materials absorb and reflect specific wavelengths, leaving dark lines in the spectrum. Analysts read those patterns to determine the chemical makeup of the dust and debris. Radar astronomy also plays a vital role. The science of deflecting asteroids is not just an academic exercise. It is a critical component of planetary defense. The Earth exists in a cosmic shooting gallery. While our planet has been struck by asteroids countless times in its history, just ask the dinosaurs, we are the first species with the intelligence and technology to do something about it. The goal of planetary defense is to find, track, characterize potentially hazardous asteroids, and, if necessary, develop the means to deflect one that is on a collision course with Earth. The DART mission was the first ever real-world test of this capability, moving the concept from theory to proven practice. It is important to understand the risks and why we undertake these missions. An impact from a large asteroid could have catastrophic consequences for life on Earth, potentially causing global devastation. While the probability of a major impact in our lifetime is low, the consequences are so high that it is a threat we must take seriously. Scientists are extremely careful to choose targets that pose no threat to Earth, either before or after the test. Planetary defense is a global effort. The successful DART mission was a beginning, not an end. It proved that humanity has the power to change the motion of a celestial body. This is a profound moment in our history. Each mission, whether it is an impactor, an orbiter, or a sample return probe, adds a new piece to the puzzle of understanding asteroids. We are learning about their diversity, their internal structures, and how they respond to external forces. This accumulated knowledge will let us build a robust planetary defense. The sky may seem tranquil and unchanging, but it is a dynamic environment that demands our vigilance. We will likely test kinetic impactors on different types of asteroids, perhaps a solid metallic body, or a much larger object to see how the results vary. One idea is the gravity tractor, a spacecraft that would fly alongside an asteroid for a long period. The tiny gravitational pull, exerted over years or decades, would slowly tug the asteroid into a safer orbit. These ancient bodies are rich in water ice, organic compounds, and precious metals. They are not just potential threats, they are also potential resources. We look to the stars not with fear, but with curiosity and a growing confidence that we can ensure the long-term survival of life on this beautiful blue marble.